Next talk is on black box constructions of time and space efficient linear arguments from Symmetric-Key primitives. And we have a journal work from Laasya, Bangalore, who's going to give the first part of the talk, Rishabh, Bhadauria, who's going to give the second part, and Kavnita Zai and Moody.
Thank you. So I'll be talking about our work on efficient sublinear arguments. So the three main properties we achieve as part of this work are, first one is we are black box, and we achieve both time and space efficiency, as well as we are just based on symmetric key primitives. If you were to relax any one of these properties, then we know how to do efficient sublinear arguments. So the novelty is essentially achieving all three together, as we will see going ahead. Zero knowledge proofs is something we are already familiar with, and Chaya has already covered, introduced this. So we'll directly jump into what this talk is about. We are interested in ZK-SNARKS with short proofs and a succinct verifier. So here succinctness basically means that we are sublinear in the running time of the RAM program. So as I mentioned, like we are focusing on the complexity of ZK-SNARKS. Mainly, we consider RAM programs with time t and use space s. So the NP statements are basically verifiable using RAM programs. The first set of works are based on time-preserving approaches, where the prover and the verifier are efficient with respect to time. Basically, the prover overhead is minimal. It's order t, whereas the verifier is polylog t. And there's a long line of works that has pushed towards making sure that the prover overhead, mainly the time, is minimal. But the downside of these works is essentially that the space complexity required is proportional to the running time of the RAM program. And if you have computations that are large and t is much larger than the space, essentially you're not efficient with respect to the space. On the other hand, you have works that are space preserving. The prover space is S, which is same as the underlying RAM program, and the verifier space is succinct, it's polylog t. So we can adapt the works of Ligero and Ligero++ to ensure that we can, the final space is just order S, but the downside here is the running time of the prover becomes polynomial NT. So this work is essentially focusing on obtaining complexity preserving ZK-SNARKS, which basically means that we want to be time preserving as well as space preserving. We're okay with quasi-linear, we ignore polylog t factors over here. So just focusing on works that are complexity preserving, first, we consider non-black box approaches. The first one is for designated verifier ZK-SNARKS. It was shown how to get complexity preserving prover and succinct verifier in the non-interactive setting by Bitansky, Kiasa, and Hogren Rothblum. And later, a publicly verifiable ZK-SNARKS were also shown by a recursive composition. And lastly, if you're willing to relax the zero knowledge property, you can get SNARKS for parallel RAM just based on symmetric key assumptions, that is collision resistant hash functions. So all these works are essentially black box, non-black box, and they make non-black box in terms of like their underlying hash function and not very efficient. So in black box setting, we have two works, Block et al., based on hardness of discrete log, and the follow-up work, which is based on hardness assumptions of hidden outer groups, where they improve the verifier. But these two works use public key primitives. Mainly, the prover is going to do at least order t exponentiations, which is which does not seem very efficient. So in this talk, as I mentioned at the beginning, we want to focus on achieving complexity preserving ZK-SNARKS in a black box way, just using symmetric key primitives. So our main theorem is we assume collision resistant hash functions, and we show that any NP relation verifiable by a RAM program that runs in time t and space s. We have the following three properties: complexity preserving, symmetric key primitives, and black box. So further, our prover has time order t and order s, where we are ignoring polylog factors. Hence, it's complexity preserving, and the verifier is sublinear in t. When t is much bigger than s, we get a verifier which runs better than order t, and the space of the verifier is polylog t. The communication is also better than t, and number of rounds are constant here. We complement our upper bound with a lower bound where we give evidence that this communication and the prover's complexities are optimal using the current techniques that we know. Basically, when I mean current techniques, we are looking at ZK-SNARKs that rely on codes. So consider a RAM program. It could also be a circuit. And the first step is to transform it into a transcript. Here, a transcript is nothing but an arrangement of the YO values for the RAM program. And this could be of size T or for a circuit of size C. And then you take the entire transcript and you encode it using codes with constant relative distance. So this is a very high level overview of the approaches, the type of approaches we are considering for our lower bound. So these techniques require a space of order T because you're encoding this huge transcript. And this is essentially our lower bound. We're saying that to encode a message of size n, you basically require space of n. So for the rest of the talk, I'll be focusing on the lower bound, and Rishabh will follow up with the construction of ZK-SNARKs for RAM. So we have a code over F2. It could be any generic field. For simplicity, we just focus on this particular field. And delta is the relative distance. So if you have a message of length n, and there is an encoding algorithm that maps it to a code word of size m. And this encoding algorithm is modeled as a RAM program, which takes time t and space s. By space s, I essentially mean the work tape, which you can think of as a scratch pad used by the RAM program during the computation of the code word. And lastly, the encryption algorithm can make multiple passes over the input. Let's call this as R passes. And just to recall, the minimum distance between any two code words is delta M, which we're going to use in our low bound proof sketch. So to quickly state our lower bound, we have for codes with constant relative distance, the encode algorithm requires a space of delta n by r. Delta is essentially constant here, and r is, you can assume it to be polylog t if you want the running time to not blow up. So essentially, the space required is of the order of the size of the message, which is n. So here, the encode algorithm has an input tape with the message and the output tape with the code, and it makes multiple passes over the input tape and writes onto the output tape. So I'd like to go over the low bound. It actually uses simple arguments, simple counting arguments. So I would like to give a very high level overview of it. First, we make three simplifying assumptions. The first one is, let's consider an encoding algorithm that just makes one pass over the input, over the message. And the second one is, let's not consider work tape at all because it's going to add it's going to make the proof slightly more involved. And the third assumption that I make is the code word head is independent of the contents of the message. So essentially, irrespective of what message you have, the code word elements written in step 1, step 2, and step 3 of the RAM program are pre-decided. It doesn't depend on the message itself. So given that we've made these three assumptions, the lower bound is as follows. The proof outline, I'll talk about the proof outline now. if you have a message of size n, the first thing you do is break it down into chunks, k chunks. Each of these chunks is of size n by k. And I'm going to vaguely define that the term influence. So I referred to a message chunk influencing a portion of the code word. Essentially, when the message head passes through this message chunk, the respective code word is written, which is depicted in this by the yellow highlighting. So the first step is we argue that there exists a message chunk which influences a small code word chunk. So if this weren't true, then we can just do a simple counting argument to say that the code word will be larger than m. So specifically, we're saying there's a message chunk H that affects code word elements less than m by k code word elements. As depicted here, it could be any of the chunks. For now, I'm just assuming it's the first message chunk that affects small portion of the code word. Now let's narrow down our focus to all the messages that only vary at the first message chunk, and all the other message chunks are the same for these set of messages. So the grayed out section is the same for all the messages, and the blue part is different. So you have 2 to the n by k such messages if you're considering F2. And this message chunk only affects the section of the code word that's shown over here. And lastly, we set the number of chunks k to be 1 by delta in terms of the constant relative distance. And if you see, you get m by k is essentially delta m. So since the messages, all the messages in the set affect the corresponding less than m by k portion of the code words, your distance is less than m by k, which is less than m delta. And the minimum distance of our coding scheme is m delta. So essentially, you're able to identify a set of messages that violate the distance property of the codes. So, so moving on, we made a lot of assumptions over here. So we try to eliminate one by one and see how it affects our lower bound. Firstly, we assume that the encoding algorithm just makes a single pass. We replace it by allowing the encoding algorithm to make R passes. So this proof essentially remains the same. All you do is in every pass, different sections of the code word get written. So you combine all these code words, group them together, and apply the exact same algorithm that I described earlier. So the second thing is no work tape is a huge constraint. If you allow a work tape of size S, and we still want the lower bound to hold. So this is slightly more involved in the sense that earlier we were able to divide the code word into chunks where each message chunk just affected a particular code word chunk. Now, if you allow a work tape, the work tape is shared between all the message chunks. So it basically affects other code word chunks. You can't clearly divide the influence of a message chunk to a code word chunk. So we prove this as follows. Because the message chunks are different at the end of every pass, we filter out the messages further and focus on only the set of messages where the work tape is same. And this again is by a very simple counting argument where you have 2 to the s possibilities for the work tape of size S and 2 to the n by k possibilities for messages, because all these messages just vary at one chunk. So by using simple pigeonhole principle, we are able to say that after every pass, the number of messages decreases by a factor of s. And after R passes, the number of messages decreases by the factor of 2 to the RS. So at the end of it, we are able to narrow down the number of messages to a small number of messages. We want to show that the set is non-empty, and for all the messages in the set, the coding property is violated. So for the set to be non-empty, we set the space to be n delta by R. So if the space is less than n delta by R, the set of messages is non-empty and it violates the coding property. So this was like the hardest part of the argument. And moving on, we have the third assumption, which is actually slightly more tricky. We want to make the code word head to be dependent on the contents of the messages, which is what happens with general coding schemes. So eliminating this assumption also uses counting arguments, but it's slightly more involved and has quite a few lemmas and claims. So we refer you to our paper for more details. This is part one of the talk, and Rishabh will be continuing with the upper bound.
Hi. So I'm Rishabh, and I'm going to talk about constructing ZK-SNARKS from RAM and basic. Oops. Yeah. And basically, I'm going to focus on the sublinear verifier with polylog space. And basically, the first step is the transformation from the RAM program to the circuit. And so what happens is that there's a transformation given by Ben Sasson et al. In 2030, where basically you convert a RAM program into a circuit transcript. And basically, there is a property of the circuit such that you can compute any information about a gate or about an intermediate wire value in polylog T or in an efficient way. And so now we're just going to convert the transcript into an extended witness, where basically we are taking the witness and we're just putting it in a matrix, where basically the number of rows is order T by S, and the number of columns are order S, because we want the proof size, we want the prover space to be order S. And so because of the uniformity of the RAM program, basically we can divide the extended witness into T by S chunks, where each chunk is of size polylog T cross S. And now basically one notation which we're going to use is flattening a matrix. So you have a matrix X, and now you want to convert it into a vector. So now what you'll do is you're going to just rearrange the matrix row by row and append it to a vector. And basically now we want to, now the extended witness here needs to satisfy some linear constraints, which is like the intra block, inter block. There's one input consistency, quadratic constraints. And again, one more efficiency aspect is that X can be generated row by row in time T and space S. So basically here you can see that all the blocks here have the same constraint. And this uniformity will be used in a proof and to reduce the verifier's complexities. And basically our protocol is built up on Ligero. So I'm just going to give a quick overview of Ligero. So you have an extended witness X, and what you want to do is you want to encode it into a encoded witness U. And basically each row of X is encoded independently, and the encoding scheme which we use is interleaf Reed-Solomon code. Now here, each row can be represented as a polynomial PI. So now if you evaluate the polynomial at the interpolation points, you get the extended witness. If you evaluate it at the evaluation points, you get the code word or the encoded witness. And here, because we want to use FFT, both the interpolation points and evaluation points have a very nice structure, which we're going to leverage later on. And so basically what we're going to do is we're going to run 3 tests on the encoded witness. First, we're going to check whether the encoded witness is a genuine code word. And then we're going to run a linear test and a quadratic test to check the linear constraints and quadratic constraints of X. So here again, the reason why we are focusing on linear test is because this is the bottleneck for the verifier as well as the prover. So here basically you can represent each constraint as AX equal to B. And now what we want to do is we want to reduce it to a inner product argument, or like a multiplication of 2 vectors. And so you multiply it with a random vector R so that you reduce it. And then what you can do is basically your X is generated by flattening a extended witness. And basically each row of the extended witness is can be represented by a polynomial. So we're going to use the same trick on the vector RTA to generate some random polynomials R1, R2, R3. And this will be combined with the extended witness polynomials to give a proof polynomial. And now the verifier will verify whether first the polynomial Q is of right degree, which is a trivial thing. Then second, it will check whether the linear constraints are satisfied. And the third, it will check whether the polynomial Q is consistent with the encoded witness U. And so our goal here is to have a sublinear verifier with polylog space. So here I'm going to make a claim that the first check and the second check, which is basically checking the degree and checking the linear constraint, can be done for free. Or you can say that it can be done in constant time and constant space. You can ask me later, but in this talk, I'm not going to explain this. So again, we're going to focus on the third check, which is the consistency check between the polynomials R and the encoded witness U. And basically here, I mean, it is written as a summation, but you can visualize it as you taking like you taking inner product between two vectors, where one is a column of U and the other is basically evaluating all the Ri polynomials at an evaluation point. And if you see here, this check, like assume that you have the polynomial Ri evaluations in your memory. In that case, the check is already sublinear and is polylog space, or like here constant, but again it hides polylog. And so basically here what we want to do is we want to focus on somehow converting the other two tasks, which is computing RTA vector and generating the evaluation of Ri vectors in a sublinear way, sublinear and polylog space. So here again, we're going to play with the uniformity of the blocks or the extended witness. So here you can see that all the blocks have the same linear constraint. And so basically you just need a single matrix A or a single constraint A. And what you can do is you can use, for all of them, you can use the same vector R to flatten them up. And this will be correct. The only thing you need to do later on is to combine them together using a random linear combiner, which is easy. So here again, we were going to use some succinctness of the circuit, wherein what we're going to say is that the matrix A is of size S cross S, and basically it's a succinct matrix. So what it means is that each column can be generated in polylog time, and the number of non-zero entries is number of constraints into polylog T. And basically you in this setting, you can compute RTA in time order S and space order 1. So this is one part. And then the second part is basically you want to compute the evaluations of Ri directly from RTA without actually interpolating and generating Ri polynomials. And so for that, we use an algorithm called D-eval algorithm, which takes in an input vector V, which you want to interpolate, and it will directly output the evaluations of P, where P is the polynomial generated by interpolating on vector V. And here, the very nice thing about our interpolation point and evaluation point is that basically it has a very nice roots of unity structure. And so you can write it, you write an evaluation as a closed form or as basically a linear combiner of the vector, where the term CK can be computed in constant time. So here the space is the number of evaluations you want to do, and the time is the vector size into the number of evaluations. So here overall, when you're gonna generate the evaluations of Ri polynomial for the test. You're gonna have a constant number of polynomials because the size of RTA was order S. And now basically the time will be order S and the space will be constant. And so now basically you have reduced each of the time of all the tasks sublinear, and you have polylog space here. And basically here we can say that here that the verifier's time is sublinear and the space is constant or polylog T. Okay. And communication is order T and rounds is order 1, but this is for this you need to read a paper. Yeah, thank you.